Hi and welcome to Module 8.4. The concept of filtering can be easily extended to two dimensions, and it carries over in a very straightforward way together with the concept of convolution, convolution theorem, and so on and so forth. In this module we will look at the class of linear space invariant filters for images, and we will see what the differences are with respect to the 1D case. One difference is that space invariant filtering is only of limited use in the case of images because images are very space variant signals. Imagine the picture of reality around you, so many different objects, so many different textures. Nonetheless, there is a class of filters that perform very simple operations such as blurring or edge enhancement that are commonly used in everyday photographic processing, and we will look at them in quite some detail. Hi and welcome to Module 8.4, in which we will talk about image filtering. We will define the concept of filtering in the context of image processing, we will classify the type of filters that we use in conjunction with images, and then we will finish with some examples. A good starting point to define the filtering operation in the space of digital images is to extend the concept of 1D filtering to 2D. And the ideas that admit a natural extension to 2D are linearity, the concept of invariance, which in the case of images becomes space invariance rather than time invariance, the concept of impulse response and its transform, the frequency response, the concept of stability, and the concept of constant coefficient difference equations, which in this case will be two-dimensional. With these ingredients, we already have a fully functional filtering paradigm for 2D signals. However, when it comes to images, the problem with linear space invariant operators is that images are a very specialized type of 2D signal. As we said before, images are designed to be interpreted by the human visual system, and as such they contain a lot of semantics which is lost on simple operators such as filters. Consider, for instance, the photograph of the scenery outside of your window. In the same picture, very many different things coexist. You have pictures of people, of cars, of building, maybe the sky, maybe some natural landscape. A space invariant filter will process every item in the same way. But it is kind of intuitive that we would like different things to be processed differently. Edges, for instance, should be treated very differently than gradients like the sky, and textures represent a new challenge altogether. Nonetheless, there are some simple operations that can be performed with standard linear filters, and therefore we will continue in the tradition of one-dimensional processing and put in place a classification of filters according to their properties. In 2D, we can distinguish as well between IIR and FIR filters based on the support of the impulse response. We can distinguish between causal and non-causal filters, and we can classify filters according to the frequency response. In particular, low-pass filters will be used to perform smoothing operation on images, whereas high-pass filters are used to enhance an image and perform edge detection. Speaking of edges, here we come to the first issue with respect to IIR filters in image processing. You remember edges are points of discontinuity in the grayscale signal, and as such they require that the phase of the Fourier components that make up the image are precisely aligned. Now, since you cannot have an IIR filter with linear phase, the result of a filtering operation will always affect negatively the edges if we use an IIR filter. A second problem with IIR filters is related to border effects. Consider the convolution operation in 1D. We have that y of n is equal to the sum for k that goes from minus infinity to plus infinity of our impulse response in k times x of n minus k. Now, if the signal x is finite support, when the index k ranges from minus infinity to plus infinity, we have to make an assumption for the values of the signal outside of its support. And usually we assume that these values are 0. So there are two border points in a 1D finite support signal, its beginning and its end. When we compute the output of the filtering operation, the choice for the value of the input signal outside of its support will influence a number of output points. If the filter is FIR and of length L, at most L points after the beginning boundary point of the signal will be affected, and the rest will be okay. If we use an IIR filter, on the other hand, because of the recursive relation, all the output will be affected by the fact that we chose some 0 values outside of the support. In a finite support 2D image, the number of border point is proportional to the square root of the number of pixels contained in the image. So the effect of the border will be exacerbated, and it will come from all sides and from all directions. So in general, we tend to prefer short FIR filters in image processing in order to minimize the effects of the border on the output image. Another issue is related to the design of stable IIR filters. You remember that in one dimension, we can check for the stability of a filter simply by looking at the position of its poles on the complex plane. However, the fundamental theorem of algebra does not hold in multiple dimensions, and therefore there is no simple way to find the roots of a multidimensional transfer function. As a consequence, there is no simple stability criterion for two-dimensional filters. A final issue with multidimensional IIR filters is computability. In other words, we have to be careful because in multiple dimensions we could come up with constant coefficient difference equations that are not computable. Here is a simple example. Consider the following filter where each output sample is computed as the linear combination of 4 previous output samples. This is what makes the filter IIR, plus the input. So here, in order to compute the output in 0, 0, we need the contribution of these 4 samples that are going to be summed together. But for instance, to compute this sample here, which is necessary to compute the output in 0, 0, we need to sum the following 4 previous output samples. Okay, so this sample now depends on this sample here, but this sample is what we were trying to compute in the first place. So we have an unbreakable self-referential loop that makes this filter non-computable. Okay, so IR filters are pretty much out for us at least. So let's look at some practical FIR filters. One of the advantages of having the whole image available for processing at the beginning is that causality is no longer an issue, as we said before. So we can design FIR filters whose impulse response is symmetric around 0, and therefore they introduce no delay. A consequence is that the number of taps of the impulse response will be odd in both dimensions. So, for instance, something like this. The per sample complexity of an FIR filter is, as we said before, M1 times M2 operations per sample, where M1 and M2 are the dimensions of the support of the filter. However, in the case of separable FIRs, this computational requirements drop down to M1 plus M2. And of course, just like in the 1D case, FIR filters are always stable. So let's revisit some classics. Moving average in 2 dimensions is a simple separable extension of the 1D moving average. Remember, in 1D we would take a window and average the samples under that window. In 2D we take a square window over the plane and we average the pixels that fall over this window. So mathematically we express that as for each output point at coordinate n1 and n2, we take the sum of all the pixels centered around n1 and n2 for an extension of 2 capital N plus 1 points in both directions. Of course, we have normalized the sum by the number of points that we use in the average, and that turns out to be 2 capital N plus 1 squared. The impulse response is again an extension of the 1D case. In the 1D case it was a simple rect. Here it's a 2-dimensional rect, where the rect extends over 2 capital N plus 1 points in both directions and is normalized by 2 capital N plus 1 squared. Needless to say, the moving average is a separable filter, and therefore the number of operations per sample will be simply 2 times capital N. We can represent the impulse response of an FIR filter in 2 dimensions as a matrix, where by convention the center tap of the filter is the center point in the matrix. So in this case, we have a moving average of 3 by 3 points, where every element in the matrix is 1, and the normalizing factor is 1 over 9. Let's try and apply the moving average to our original image, which is a 256 by 256 picture. Here we have a moving average of side 11 pixels, and we can see that the effect is to blur the original image. If we push the dimension to 51 points, the blurring becomes very severe. You can see here around the image the effect of the border that I mentioned before in the context of IIR filtering. This is the width of the impulse response, and we see this discontinuity because after 51 points, the zeros that we assume to be outside of the original image no longer influence the output of the moving average filter. Another popular low-pass filter for images is the Gaussian blur. In the Gaussian blur, we take an impulse response, which is a two-dimensional Gaussian function. A cross-section of this impulse response, if we were to plot it, would look like this, the typical Gaussian characteristic. So this filter computes a moving average where the pixels away from the center of the filter are weighed by a Gaussian characteristic. Now, the Gaussian function, whether one or two-dimensional, is not a finite support function, so we arbitrarily truncate it and set the impulse response to 0 after big N minus 1 samples, where big N is approximately 3 times the standard deviation of the Gaussian characteristic. If we were to plot the impulse response in Cartesian format, it would look like this. We can also plot it as an image, and here you can see that we're weighing more the points that are close to the center of the filter and weighing less the points that are close to the corners. The Gaussian impulse response has a perfect circular symmetry, and so it is separable. You can implement it as a horizontal Gaussian filtering followed by a vertical Gaussian filtering in one dimension. The result is that we're less sensitive to border effects. By appropriately choosing the standard deviation and the support of the filter, we can achieve arbitrary smoothing power. Here, for instance, we have a Gaussian filter with a standard deviation of 1.8, so we choose N in this case to be approximately 3 times this, we choose that to be around 5, and so we have an 11 by 11 square filter. Here, the standard deviation is 8.7, and we choose N to be 25 in order to get a 51 by 51 blurring filter. Now you can see that because of the smoothing characteristic of the Gaussian impulse response, we're less affected by border effects. There is still a darker halo around the border of the image, but it's less pronounced because as we move inwards, the zeros outside of the image are weighed down by the Gaussian characteristic. Let's now look at some high-pass filters for image enhancement. The Sobel filter is a high-pass filter that computes an approximation to the first derivative either in the horizontal or in the vertical direction. Let's look first at the horizontal Sobel operator. This is a 3 by 3 FIR filter, which we can express in matrix form as such. Remember, the center item in the matrix corresponds to the origin of the filter. It turns out that the Sobel operator is separable, and it is composed of a vertical filtering operation on 3 taps given by this impulse response, followed by a horizontal filtering operation on 3 taps given by this impulse response. Now you remember we have seen in module 6.6 that the impulse response of a discrete time differentiator is like so: h of n is equal to 0 in 0, and equal to minus 1 to the power of n over n for n not 0. So this 3-tap filter here is the 3-tap approximation of the ideal differentiator in discrete time. The first part here is a 3-tap low-pass filter. The impulse response looks like so. And what this filter does is average together 3 subsequent lines in the image before we computed the differentiation. This helps us combat the noise that a simple differentiation operation would end up amplifying. The vertical Sobel filter approximates the derivative in the vertical direction, and its impulse response is simply the transpose of the horizontal Sobel filter. If we now apply the Sobel filter to our usual image, we can see that, as we expect from a differentiation operator, the uniform areas are sort of cancelled out, and the points of discontinuity, such as the edges, are enhanced. In particular, the horizontal Sobel filter approximates the derivative in the horizontal direction, and therefore is particularly sensitive to vertical lines. So here you see that these lines in the vertical direction are enhanced. Conversely, the vertical Sobel filter differentiates in the vertical direction and therefore will enhance the horizontal lines, or the lines that go pretty much in the horizontal direction. We can combine the effect of horizontal and vertical differentiation into the Sobel operator, which is an approximation of the square magnitude of the gradient. The operator called operator because it's not a linear filter. It's indicated by the symbol nabla, which applied to an image x of n1 and n2 gives the square magnitude of the horizontal filter's output plus the square magnitude of the vertical filter's output. If we apply the Sobel operator to the image, we obtain what we see here on the left. It is customary to threshold the image on the left and to reverse the role of black and white in order to obtain a contour image. In other words, this image here, y of n1 and n2, can be defined as 0 if the Sobel operator is greater than a certain threshold, and 255 if it's less than a certain threshold. In other words, this image here on the right can be defined as such. The pixel at coordinate n1 and n2 will be equal to 0 if the Sobel operator is greater than a given threshold, and it's going to be equal to 1 otherwise. Finally, let's have a look at the Laplacian operator in image processing. So if we have a function in continuous space, a function of two continuous variables t1 and t2, the Laplacian is defined as the sum of the two second-order partial derivatives with respect to the variables of the function, the unmixed partial derivatives as they're called. The Laplacian in this case measures the curvature of the function interpreted as a surface in 3D space. And so a high value for the Laplacian indicates a point of high curvature. Now, if you consider that an image is a curve in 3D space, where the level of the curve indicates a grayscale level of the image, then a region of high curvature most likely indicates an edge. So the Laplacian operator gives us another way to find edges in an image. But before we can apply the Laplacian operator to digital images, we have to find a discretized representation for this operator. To do so, we start by considering the Taylor expansion of a generic function of one variable, f of t. And we can write f of t plus tau, where tau is a small increment, as the sum, for n that goes from 0 to infinity, of the nth derivative of f computed in t divided by n factorial and multiplied by tau to the power of n. We now use Taylor's expansion formula to compute the values of f in t plus tau and t minus tau. So in t plus tau, we start the expansion and we stop at the second order term, and we get f of t plus f prime of t times tau plus 1/2 second derivative of f in t times tau squared. And for t minus tau, we get exactly the same formula with the difference that the sign here changes. Now, if we sum these two things together and we rearrange the terms, we get an approximation for the second order derivative of the function in t that can be expressed as 1 over tau squared that multiplies f of t minus tau minus 2 times f of t plus f of t plus tau. Now this is a linear combination of three values of the function f computed at regularly spaced intervals on the plane, namely in t minus tau, t, and t plus tau. So they're all separate by an interval of width tau. So if we now go to the integer grid by setting tau equal to 1, we can see that this is nothing but a 3-tap FIR filter of impulse response 1, minus 2, 1. So we can approximate the second derivative at a given point with a zero-centered FIR filter like so. Now let's translate this in the case of an image. Remember, we're trying to approximate the Laplacian, and of course the Laplacian is, for a function f, the sum of the partial derivatives of second order. So first of all, we have to embed the one-dimensional FIR that we just found into a 2D filter, right? So if the impulse response for one dimension is 1, minus 2, 1, well, we can always convert this by putting zeros everywhere, right? So we would have 0, 0, 0 here, 1, minus 2, 1, 0, 0, 0. And this gives us an approximation of the second order derivative, horizontally speaking. The vertical component will be just a transpose of this, And if we sum these two guys together to obtain the Laplacian, we have a 3×3 FIR approximation to the gradient with this impulse response. If we now apply the Laplacian to our usual image, we get an enhancement of the points of discontinuity. To make this more visible, we first threshold the result of the Laplacian operator, and then we reverse the roles of black and white, and this is the image that we get.